Okay, so I'm going to talk to you about some research I've been doing on earthquakes in the Pacific Northwest and the effects that they could have on bridge columns. So this is a project that I'm working on with my colleague Adam Phillips. And then you see a list here of a number of students that have graduate students who have helped us with this work. Sean, Stacia, Zach, William, and Ruben. So I'd like to kind of highlight a number of different things that we've been doing with this project, and I don't think we'll have time to talk about any of them in too much detail, but just kind of want to go through what I can. We've done some testing, we've done some modeling, and we've also run some time history analyses, so simulations to predict failure probability of these bridge columns. So a little bit about the topic. We have a lot of bridges in the US that were built back in the 50s and the 60s during the highway program. And a lot of those bridge columns are deficient. So there's been an effort to try to retrofit those bridge columns. So one approach that has been used is to put steel jackets around the bridge column, and that's a technique that WSDOT has been using, and also it's been used in California as well. And there has been a lot of research on this topic. So on the left, you see these are called load displacement plots for columns. And what you're seeing here is that the column, if you push it a little bit, it reaches its strength and it quickly loses its strength. If you retrofit it, you can get it to maintain and hold that strength through a very large range of displacement. And this is what we want in the earthquake. So a lot of these bridges were built a long time ago before we knew all this stuff about seismic design. And so now we're trying to retrofit them to enhance the behavior and keep them standing during large earthquakes. WSDOT has been using this technique for a while. So you see some figures here about kind of timeline. They started back in 1991, and the amount of dollars that have been spent on this program up to this point, quite a lot of money. The big issue here, the research I had shown was done back in the 90s, but one of the big issues that we're seeing here in the Northwest is a concern that we have the potential for very long duration earthquakes. So we're concerned about a magnitude 9 Cascadia subduction zone earthquake. Seismologists have been studying this, are continuing to study this, and they have recently increased the seismic hazard in this part of the country. And these subduction zone earthquakes also tend to be long duration events. So there's some characteristics of the motions that we need to think about as well with the retrofitted column. So with those two concerns in mind, we've set out to study the behavior of retrofitted bridge columns in this region here in the Pacific Northwest, subjected to Cascadia subduction zone earthquake. So one of the first things we did in the project, we wanted to run some experiments, collect some data that we could then use on its own as test data, but also use it to support some modeling work that we were doing as well. So one of the early steps was to characterize WSDOT's inventory. And so WSDOT was kind enough to give us access to their bridge inventory. And so we were able to go through and look at the columns that they have retrofitted at this point. We could also get access to details of other columns that they have not retrofitted. But we were able to characterize some of the properties of those typical properties of those columns and come up with a testing plan to test 6 columns that we thought were fairly representative of what's out there in Washington state inventory. So you see some of the test variables there. We're looking at differences in the amount of rebar in the column cross section, the axial load on the column, which is the gravity load that column is holding up, and also differences in the height of the column. So look at the different columns that we had tested. There you see one tall column, as well as some of the other ones. There were a few duplicates because if you jump back to this, we also varied the loading protocol a little bit too, which I'll show that in a bit. So some details of the footings. The footings were actually designed as strong footings. And that's important because there's a lot of concern also about weak footings out there in the field. So we didn't simulate that condition. We studied a strong footing condition, but I think certainly we would like to do some follow-up research to look at what to do about the weak footings that are out there in the field. So I'll go through this pretty quickly, but just some photos showing the construction. We built these on site. We tested them in our lab. And so here's installation of the steel jacket. In the field, this is usually installed as two semicircles that are welded along the seam up the height of the column. We kind of cheated a little bit. We dropped them over from the top. It just made things a little easier for us to get them constructed. But you see the jackets there, they were, I believe, 3/16 of an inch thick. Okay, so not really that thick, but it was just a plate of steel that had been rolled into a circular shape and welded. So we're dropping those over the column, and that's what they look like as we completed the process. You can see some little nozzles here. They were used to get grout inside of the column. So the jackets are typically oversized, and you use pressurized grout to fill the cavity between the column and the jacket. So the whole idea here is to really provide confinement of the concrete to prevent it from crushing or to mitigate the likelihood that it will crush, more so than to enhance strength. We're not really trying to enhance flexural strength of the column, but we want to be able to maintain the strength of the concrete in order to kind of sustain that strength of the column and give it a nice ductile behavior. And then finally, we put these little kind of cap blocks at the top because we needed them in order to apply load into our columns when it came time to run the tests. So this is showing steel reinforcement properties. One of the interesting things is as we went through the inventory and looked at what was out there, a lot of this stuff was built in the 60s, 70s, and it used older reinforcement. So it's not consistent with modern day grade 60, it was older grade 40 reinforcement. So we worked with Nucor over on the western side of the state, and they made for us a special batch of grade 40 reinforcement and higher bar sizes, and we used that in our test columns. So we did some material testing here just to kind of verify the properties of that grade 40 bar. So here's a look at our test setup. They were tested as cantilever columns, and we did apply a axial load on the column. So that simulates that gravity load from the tributary portion of the bridge that the column is holding up. And then we cycled it back and forth using the lateral actuator. We anchored it down to our strong floor. So there's a little look at the top. One of the things that we really wanted to try to simulate was a fairly realistic P delta condition where we would let that gravity load roll along. So we had a roller set up there to allow it to roll along and continue to apply the load downward during the test. So there's a look, sorry, not the best photo, but there's a look at what that test setup looked like in the lab with the lateral load being applied from that large actuator and the specimen anchored down to the floor. So we used a standard cyclic loading protocol, though we actually had done some analysis to assess the number of cycles to use. I had mentioned that there's concern in this region about the long duration nature of the Cascadia earthquake. And so we actually we increased the number of cycles relative to a lot of standard cyclic protocols. But this was kind of our default protocol. Then we took one column, which was identical to our benchmark column, and we examined what would happen if we ran an earthquake protocol. So we ran a model to get the behavior of a bridge column in a Cascadia subduction zone earthquake, and we then fed that into the test for one of our columns. So a look at characteristic damage. The columns performed really well. The jacket prevented crushing of concrete at the location where the jacket was present, but we did eventually get some kind of breakout of concrete in the footing. and most of that spalling did not really go beyond the level of the rebar. So it was just cover concrete damage that you're looking at here. And this was a fairly advanced level of deformation, 15 times delta Y. It's pretty big. So we were out probably on the order of maybe 5% drift, 6% or something like that at this point in the test. And this is what it looked like at the completion of testing. So again, very little damage in the column. We are getting some damage right at that interface between the column and the footing. So the main source of strength degradation in the test was fracture of rebar, the vertical bars in the column. So we went through and kind of characterized when each of those fractures occurred in the test, because we then wanted to be able to model and simulate that and eventually have a model that we could use as a predictive tool if we ran some ground motions into that model. So the study started to then focus quite a bit on fatigue behavior of the reinforcement. We did this for each of the 6 columns. You could see the load displacement here, response for each column. And again, we're able to come up and really maintain that strength through a large displacement. So it's a very favorable characteristic in an earthquake. So overall, I would say they performed pretty well. And the source of failure, the source of strength degradation eventually was rebar fatigue. Now we also tested some, this was more recent. We haven't prepared as many results on this yet, but we also tested a set of 6 columns with FRP jackets. So you see one of those here. I think this is actually a video. Let's go ahead and just let that run. But this will show it just getting sight, and we've sped it up. We test a lot slower than this typically, so we can mark cracks and things like that. But this is an FRP jacketed column. We tested another group of 6 of these, and 5 of the 6 were identical to the steel jacketed columns. So that let us really make a direct comparison of the jacketing techniques. Back when WashDOT started doing this, carbon fiber was pretty expensive. The price is going down these days, so I think this could be a viable option. The black lines that you're looking at here are data from the FRP jackets. The red lines are coming from the steel jackets. So you can actually see that the deformation capacity was bigger in our set of experiments for the FRP jacketed columns. So not sure that it's necessarily saying that one is better than the other, but I think it does show that both options could be considered. And up to this point, WashDOT has really favored the steel jackets. So just a table here showing deformation capacity. We were reaching pretty big levels of drift, 5%, 6%, before we fractured that first bar and we started to see the onset of strength degradation. We took a few of them out to the point where they were near collapse, and that was out clear at like 10% drift. So we had quite a high deformation capacity coming through on those columns. Looks like I'm getting a little tight on time here. Let me jump ahead a bit. But we did do some work on the fatigue of the reinforcement, just recognizing the importance of that in the overall behavior. We actually had WashDOT send us some sample rebar from demolished bridges. And one of the things we wanted to look at is how does the fatigue of that compare to the stuff that Nucor had sent us? Because even though Nucor was making a grade 40 bar, you know, it doesn't really simulate 60 years of service in the field or whatever it was. So we had some samples of both. We were able to do some fatigue testing and compare the fatigue parameters. And sure enough, the stuff that WashDOT sent was a bit more brittle, a bit more fatigue prone than the stuff that we had been using from Nucor. So then a big focus became, okay, what do these fatigue parameters look like? We took our test data, we did some curve fitting using some traditional approaches for fatigue. And we got these parameters here, capital M and little m. And we had those for the old bar, we had those for the new bar. Well, then
we have 2 minutes left, Chris.
Okay, I'll go quickly through the rest then. So then we wanted to fit a model to the test data that we could then use as a predictive tool. And the model did include fatigue. So we could update those fatigue parameters, whether we were modeling old column versus new column. But the model really accounts for, so we had a plastic hinge model that accounts for the deformation in that hinge where it's concentrating. And we modeled this in a program called OpenSeas, which allows for the input of fairly detailed material properties for concrete and steel with cyclic effects considered. And it also allows you to get pretty good information on stress and strain and rebar and things like that. So we were able to model, these are 3 of the columns that were tested at the University of San Diego, California back in the 90s. We're getting a pretty good fit between the model and the test. The blue dot, it's a little hard to see. That's our prediction of fracture of the first bar. So for us, that would be the onset of strength degradation. So we're a little maybe conservative on our prediction relative to the test. And there's where we're at with regard to our test. So once again, I think our blue dot is a little conservative. The overall model is fitting pretty well in terms of the hysteretic shape. So last item here, once we had that model to a point where we felt pretty good about it, you know, it's given us a prediction of when that first bar fractures, which again, kind of conservative estimate of when these columns are going to strength degrade. We did some fragility analyses. So we came back and we used the, you know, a range of parameters that were characteristic of washout bridges without getting carried away. We wanted something that we could, you know, reasonably get through the analysis. So we selected columns to cover washouts inventory, and we ran ground motions through those column models. We actually used single degree of freedom models for those analyses. We're looking at extending that into multi-degree of freedom models to see how much we compromise the accuracy by using single degree of freedom. We ran it for a range of periods, a range of strength values, and when we looked at, we used actually synthetic ground motions for Western Washington. So these were provided to us by a team from the University of Washington and the US Geological Survey. So simulated motions for a full rupture of the Cascadia subduction zone. You see 10 sites here that are located in Western Washington. We were able to run that for all these different combinations of period and strength in our single degree of freedom model, and use that to estimate when we were getting failures. So you see some just sample results here. We're still working through this, but locations out near the coast, it appears that short period bridges are maybe a bit more prone to failure. And then as you move into Seattle, we're actually getting an interesting effect from the basin that's in Seattle, the sedimentary soil basin. So you're seeing increased probability of the potential for maybe the onset of failure is even a better way to describe it, because we're using some fairly conservative metrics here. But you see, you know, you do see increased likelihood as you get to longer period as you enter that sedimentary basin in Seattle. So with that, I will wrap up, and we've been putting together these charts that show that estimated failure probability at different locations around the state. So some conclusions there. You know, the columns performed pretty well. We reached pretty high levels of ductility. We did find that the older bar was more fatigue prone. So we then made that adjustment in our modeling when we carried out the regional prediction. So we'd like to extend some of this work a bit further. We'd like to include multi-degree of freedom. We'd like to try to actually map it to bridges in Washington and work in Oregon as well. So with that, I'll conclude. Thank you. And if you have any questions, I'd be happy to answer them.